On October the 9th, 2025, at 14:47 Universal Time, NASA's Solar Orbiter mission recorded something that shouldn't exist. A cluster of subcoronal jets, high-velocity plasma streams, emerged from a depth of 2.9 million kilometers beneath the Sun's visible surface. That's deeper than the convection zone boundary, deeper than any jet source we've ever mapped, deeper, in fact, than our models say plasma jets can physically form. The instruments didn't malfunction. The data went through 3 independent verification chains at the European Space Agency's Solar Operations Center in Madrid. The readings were confirmed by NOAA's Space Weather Prediction Center and cross-referenced with archived SOHO magnetograms spanning 2 solar cycles. Every check came back consistent. These jets exist, and they exist in a place where our understanding of stellar physics says they cannot. But here's what makes this more than an observational curiosity. Here's what keeps solar physicists awake now, checking their email at 3 in the morning. The chemical signature of those jets doesn't match solar composition. Spectroscopic analysis reveals traces of oxygen-18, a heavy isotope, in ratios that align not with the Sun's well-documented elemental fingerprint, but with cometary debris, or with something that entered our solar system from beyond the heliopause. The timing is not gentle with us. Solar Orbiter's inner perihelion window closes in 47 days. After that, the spacecraft begins a 6-month recalibration arc that will take it out of observation range for these specific coronal depths. What we learn in the next 7 weeks may be all we learn for years, and there's a name surfacing again in the data logs, a name that appeared in 2023, briefly commanded headlines, then faded into the background hum of cosmic traffic. A name that carries with it a trajectory we thought we understood, until it started showing up in places it shouldn't be. 3 Atlas, an interstellar object, a visitor from beyond, a comet, we were told, a wanderer passing through, obeying the ordinary laws of gravity and light pressure, destined to sling past the sun and vanish back into the dark between stars. Except it didn't behave that way. And now, 2 years later, as these impossible jets bloom beneath the sun's surface, that name is back in the data. Not as speculation, not as fringe theory, as isotopic evidence, frequency patterns, and thermal echoes that refuse to resolve into coincidence. Something is moving beneath the sun, something casting shadows no star should make. Before we go deeper, hit like, subscribe, and tell me where you're listening from, because this story is still unfolding, because the data is coming in faster than the explanations, because 47 days is not a long time when you're trying to rewrite the physics of stars, and because what we're about to walk through together isn't just another space mystery, it's a sequence of events, dated, documented, and verified, that began with a single frame of solar data and has since woven itself through Mars dust grains, radio silence over the Pacific, missing files in NASA archives, and a thermal bridge that shouldn't exist in the vacuum of space. This is not science fiction. This is October 2025. I'm your host, and this is Beyond the Solar Veil. Chapter 1. The Jets That Shouldn't Exist. The European Space Agency's control room in Darmstadt, Germany, is not built for drama. It's built for precision. Rows of monitors display telemetry and scrolling columns. Engineers speak in clipped technical shorthand. The lighting is fluorescent, steady, and practical. When something extraordinary happens here, it doesn't arrive with alarms or flashing red lights. It arrives as a graph that doesn't fit the model. That's what happened on October 9th. Dr. Helena Rask, a solar physicist with ESA's Solar Orbiter science team, was reviewing high-resolution imagery from the spacecraft's Extreme Ultraviolet Imager, EUI for short. Solar Orbiter had been stationed in a tight perihelion orbit, looping closer to the Sun than Mercury, capturing imagery of the corona at wavelengths invisible to human eyes. The mission's goal was to map the dynamic processes that drive solar wind, coronal mass ejections, and the mysterious heating of the Sun's outer atmosphere. Routine work, precise work. The kind of science that unfolds in increments, dataset by dataset, over years. But on October 9th, EUI captured a sequence that made Dr. Rask stop scrolling. A cluster of bright jets, thin, luminous streams of plasma, was emerging from deep within the Sun. Not from the chromosphere, where such jets are common, not from the photosphere, the visible surface where sunlight is born. These jets originated from the subcoronal region, a layer nearly 3 million kilometers below the surface we see when we look at the sun with our eyes. That depth places the origin of these jets below the convection zone boundary, the churning layer where hot plasma rises and cool plasma sinks, generating the magnetic fields that shape solar activity. Below that boundary, the plasma is so dense, so compressed by the weight of the star above it, that it shouldn't be able to eject material upward with the velocity these jets displayed. Yet there they were. Bright, fast, undeniable. Dr. Rask flagged the data for secondary review. Within 2 hours, 3 independent teams at ESA, NOAA, and the UK's Rutherford Appleton Laboratory had confirmed the observation. The jets were real. The depth was real. The velocity, measured at over 400 kilometers per second, was real. And then the questions began. Solar jets are not rare. They occur constantly across the sun's surface, driven by magnetic reconnection events, moments when twisted magnetic field lines snap and release energy in violent bursts. These jets typically form in the corona or upper chromosphere, where the plasma is hot but diffuse, allowing material to be accelerated along magnetic channels and ejected into space. But these jets were different. They formed too deep. They moved too fast. And when the spectroscopic data came back from Solar Orbiter's SPICE instrument, designed to measure the chemical composition of solar plasma, the mystery deepened into something stranger. The jets contained oxygen-18. Oxygen-18 is a stable isotope, heavier than the more common oxygen-16. In solar science, isotopic ratios are fingerprints. They tell us where material came from, how it formed, what processes shaped it. The sun's oxygen is well characterized. Decades of observation have given us a precise isotopic profile, about 99.76% oxygen-16, with trace amounts of oxygen-17 and oxygen-18. The jets matched that profile. Almost. The oxygen-18 ratio was elevated, not by much, but enough to register as anomalous, enough to suggest that the plasma in these jets had been contaminated by material that didn't originate in the sun's core. Cometary material, for instance, often carries elevated oxygen-18 ratios. When comets formed in the cold outer regions of the early solar system, or beyond, the isotopic processes that built their ice and rock left a distinct chemical signature. If a comet were to pass close enough to the sun, its tail could seed the solar atmosphere with foreign isotopes. But no comet had passed that close recently, and even if one had, the contamination would appear in the corona, the outermost layer, not nearly 3 million kilometers deep. Unless something else was happening. Dr. Rask reviewed the timeline. October 9th. The date felt familiar. She opened the mission's broader observation logs, cross-referencing solar activity over the previous month. What she found was subtle, but striking. The jets had emerged during a magnetic lull. Solar activity follows an 11-year cycle, oscillating between solar minimum, when the sun is quiet with few sunspots and minimal flares, and solar maximum, when the surface roils with magnetic storms. October 2025 was deep in solar cycle 25, approaching the peak of activity. The sun should have been loud, magnetically turbulent, covered in active regions. But on October 9th, for a span of roughly 6 hours, the sun's magnetic output dropped. Not dramatically, this wasn't a shutdown, but measurably. The global magnetic field strength dipped by approximately 8%, a fluctuation within normal bounds but unusual in its timing and symmetry. And during that lull, the jets appeared. It could be coincidence. Solar physics is full of correlations that dissolve under scrutiny. But Dr. Rask noted the timing in her report anyway, flagging it for further analysis. Then she did something that would later prove more significant than she realized. She searched the ESA archive for similar events. She found one. A single match. A subcoronal jet cluster recorded by the Solar and Heliospheric Observatory, SOHO, in September 2022. Same depth, same velocity profile, same brief magnetic lull preceding the event, and in the metadata, a note from the original observation team: spectral anomaly, elevated O18 detected, origin unclear, recommend follow-up. No follow-up had been conducted. The data had been archived, marked as low priority and filed away. Solar science generates terabytes of information daily. Not every anomaly can be investigated. Some mysteries are shelved, waiting for context. On October 9, 2025, that context arrived. Dr. Rask pulled the 2022 data and overlaid it with the new observations. The match was almost exact. Not just in depth and velocity, but in the spectral signature. The same oxygen-18 elevation, the same isotopic fingerprint. She drafted an email to the Solar Orbiter mission's principal investigator, Dr. Jean-Claude Moreau. She kept the language careful, clinical, speculative. Possible recurring phenomenon. Recommend isotopic comparison with archived cometry data. Then, almost as an afterthought, she added a final line. Check 3i Atlas observation logs. She wasn't sure why she wrote it. 3i Atlas had been an interstellar comet, detected in late 2023 as it fell toward the Sun on a hyperbolic trajectory. It had been observed, catalogued, and tracked as it whipped past the Sun at perihelion and began its outbound journey back to interstellar space. It was interesting. Any interstellar object is, but not alarming, not mysterious. Except for one thing. During its close approach to the Sun, 3i Atlas had exhibited a brief, unexplained acceleration. Not from outgassing, comets do that naturally as they warm, but from something else. The acceleration vector didn't align with solar radiation pressure. It didn't match any known cometary behavior. It was small, a fraction of a % change in velocity. But it was there, documented in tracking data from multiple observatories, and it had happened in September 2022. Dr. Rask stared at the two dates on her screen. September 2022, October 2025. 2 subcoronal jet events, 2 oxygen-18 anomalies. And in the space between them, a visitor from beyond the solar system moving through the inner heliosphere on a trajectory no one fully understood. She sent the email. Later that day, Dr. Moreau replied. His response was brief. Interesting correlation. We'll flag for mission review. In the meantime, let's not speculate publicly. We need more data. That restraint is standard in science. You don't announce mysteries until you've exhausted the explanations. You don't claim anomalies until you've verified that your instruments didn't lie, that your models didn't miss something, that the universe isn't simply doing what it's always done in a way you haven't noticed before. But deep in the observation logs, in the metadata streams that flow between instruments and servers, a pattern was beginning to take shape. A pattern that linked the Sun's deep interior to the cold dark of interstellar space. A pattern that suggested something had passed through the solar system, not once but repeatedly, and left a mark. Not in the corona, not in the solar wind, but beneath the surface, in the plasma depths where stars keep their secrets. On October 9th, we saw those secrets begin to surface. Meanwhile, across the scientific community, the data began its slow circulation. Solar Orbiter's findings were distributed to partner institutions, NASA, JAXA, the European Southern Observatory. Researchers in heliophysics, plasma physics, and stellar dynamics received the raw data packets, each group approaching the mystery from their own disciplinary angle. Some dismissed the jets as a transient magnetic anomaly, rare but explicable within the known parameters of solar convection. Others suggested instrument calibration drift. Perhaps the depth measurement was off, and the jets were forming higher in the solar atmosphere than the telemetry indicated. But a smaller group, the ones who pull up archived data at 2 a.m. because something doesn't sit right, began asking different questions. Why did the jets appear during a magnetic lull? Why did the oxygen-18 ratio match cometary material? And why did the timing align so precisely with 3i Atlas's previous perihelion passage? These weren't rhetorical questions. They were the kind of questions that reshape research agendas, that redirect funding, that turn quiet careers into urgent quests for answers. And they were questions that didn't yet have answers. Not on October 9th. Not yet. Chapter 2. The Quiet Frequency. 2 days after the jets appeared, a radio telescope in New Mexico picked up a sound that shouldn't have been there. The Carl G. Jansky Very Large Array, VLA for short, is a collection of 27 radio dishes arranged across the plains of the San Agustin Basin. Each dish is 25 meters wide, painted white, mounted on rails that allow the array to reconfigure itself depending on the observation campaign. Together they form one of the most sensitive radio observatories on Earth. capable of detecting faint emissions from distant galaxies, pulsars, and the cold molecular clouds where stars are born. On October 11th, the VLA was conducting a routine survey of solar radio emissions, monitoring the sun's output across a broad range of frequencies. Solar radio bursts are common during periods of high magnetic activity. Coronal mass ejections, flares, and active regions all emit radio waves as charged particles spiral along magnetic field lines. The VLA's job was to catalogue these emissions, building a database that helps scientists understand how energy flows through the sun's atmosphere. At 0322 Universal Time, the array detected a signal at 37.8 MHz. It lasted 19 minutes. Radio signals from the sun are typically broadband. They span a wide range of frequencies, creating a wash of noise across the electromagnetic spectrum. Narrow-band signals, concentrated at a single frequency, are rare in solar observations. When they occur, they usually indicate a specific plasma process, electron beams, shock waves, or density fluctuations in the corona. But this signal was different. It was clean, stable. It didn't drift or fluctuate the way natural solar emissions do, and it was synchronized, perfectly synchronized, with the timing of the subcoronal jets that Solar Orbiter had recorded 2 days earlier. Dr. Yuki Tanaka, a radio astronomer with the National Radio Astronomy Observatory, was on duty that morning when the detection came through. She reviewed the data, checking first for terrestrial interference. The VLA is located in a radio quiet zone, protected by federal regulations that limit broadcast from nearby sources, but contamination still happens. Satellites, aircraft, even distant cell towers can leak signals into the array's receivers. Dr. Tanaka ran the standard filters. She checked the phase calibration, looking for patterns that would indicate a ground-based source. She cross-referenced the signal with known satellite frequencies, military radar bands, and commercial broadcasts. Nothing matched. The signal was coming from the direction of the sun, and its frequency, 37.8 MHz, was below the ionospheric cutoff, meaning it shouldn't have been able to propagate through Earth's atmosphere from a terrestrial source anyway. If the signal had originated on Earth, it would have been absorbed or reflected by the ionosphere long before reaching the VLA's receivers, which meant the signal was real. It was coming from the sun, or from something near the sun. Dr. Tanaka flagged the detection and forwarded the data to the VLA's solar observation team. Then she did something that protocol doesn't strictly require, but experience teaches. She pulled up archived observations from the past 3 years, searching for similar signals. She found nothing. The 37.8 MHz frequency had been monitored continuously, and no comparable emission had been recorded. Whatever produced the signal on October 11th, it was either new, or it had been silent until now. But there was one detail that caught her attention. The signal's phase, the alignment of its electromagnetic wave peaks and troughs, matched the magnetic oscillations recorded by Solar Orbiter during the jet event on October 9th. Not approximately, exactly. In radio astronomy, phase matching is rare. When two signals share the same phase, it suggests they originate from the same source, or are driven by the same underlying process. A random coincidence would produce mismatched phases, scattered across the timing spectrum. But this signal and the solar jets were locked together, as if one were the echo of the other. Dr. Tanaka noted this in her report. Then she added a speculative line, the kind that makes senior scientists wince but young researchers can't resist. Possible correlation with subcoronal jet event. Recommend follow-up with ESA Solar Orbiter team. The report circulated. Within 48 hours it reached Dr. Rask's desk in Darmstadt. She read it twice. Then she opened the 3i Atlas observation logs. 3i Atlas had been discovered on December 18, 2023, by the Atlas Survey System, Asteroid Terrestrial Impact Last Alert System, a network of telescopes designed to detect near-Earth objects. The discovery images showed a faint, fast-moving object with a slightly fuzzy appearance, suggesting outgassing. Follow-up observations confirmed it was a comet on a hyperbolic trajectory, an orbit that indicated it had come from outside the solar system. Interstellar objects are rare. As of October 2025, only 3 have been confirmed, 1 Oumuamua in 2017, 2 Borisov in 2016, and 3 Atlas in 2023. Each one generated intense scientific interest, not just because they came from beyond, but because they offered a glimpse of planetary systems we can't yet reach. Studying their composition, structure, and behavior tells us what's out there, drifting between the stars. 3I Atlas was catalogued, tracked, and observed as it fell toward the Sun. Spectroscopic analysis revealed it was a comet, ice and rock, typical of objects formed in the outer regions of a planetary system. Its coma, the cloud of gas and dust surrounding its nucleus, displayed water vapor, carbon monoxide, and trace organics. Nothing unusual, but as it approached perihelion, the closest point in its orbit to the Sun, something changed. On September 14, 2022, as 3I Atlas swung past the Sun at a distance of 0.38 AU, about 57 million kilometers just inside Mercury's orbit, multiple observatories detected a brief acceleration. The comet's velocity increased by approximately 0.03% over a span of 12 minutes. That's a tiny change. In absolute terms, it amounted to a velocity increase of less than 10 meters per second. But in orbital mechanics, tiny changes matter. They accumulate, they shift trajectories, and when the acceleration doesn't match any known natural process, they demand explanation. The most common explanation for cometary acceleration is outgassing. As a comet warms, ice sublimates, turns directly from solid to gas, creating jets that act like tiny rocket thrusters. This effect, called the rocket effect or non-gravitational force, is well documented and accounted for in orbital predictions. But 3I Atlas's acceleration didn't align with outgassing. The direction was wrong. Outgassing jets typically push a comet away from the Sun, along the axis of sunlight. 3I Atlas's acceleration was perpendicular to that axis, as if something had nudged it sideways. Researchers proposed several explanations: uneven outgassing from a rotating nucleus, a fragment breaking off and imparting momentum, interaction with the solar magnetic field, though that's usually negligible for comets. None of the explanations were fully satisfying, but 3I Atlas was moving away, fading as it returned to interstellar space, and the data was limited. The mystery was noted, discussed briefly in a few conference presentations, and then filed away as one of those small anomalies that populate the edges of science. Until October 11th, 2025. Dr. Rask pulled the archived radio data from the VLA's 2022 observations, searching for any emissions recorded during 3I Atlas's perihelion passage. Most of the coverage had been focused on higher frequencies, gigahertz ranges, where molecular emissions from the comet's coma would be visible. But the VLA had been conducting a simultaneous low-frequency solar survey, the same kind of routine monitoring that had picked up the 37.8 MHz signal in 2025. She found the file, she opened it, and there it was, a 37.8 mWh emission, 19 minutes long, detected on September 14, 2022, beginning at 09:14 UT, exactly 14 seconds before 3I Atlas's unexplained acceleration. Dr. Rask sat back in her chair. She stared at the screen. 2 events, separated by 3 years, both involving subcoronal jets, oxygen 18 anomalies, and a 19-minute radio hum at 37.8 MHz, and both occurring within hours of 3I Atlas's closest approach to the Sun. She opened a new email to Dr. Moreau. She typed, "We need to talk." The conversation that followed wasn't recorded, but the outcome was. Within a week, ESA convened an internal working group to review the correlation between solar orbiters' jet observations and the 3I Atlas data. The group included solar physicists, radio astronomers, and orbital dynamicists. Their mandate was simple: determine if the correlation was meaningful or coincidental. Science operates on skepticism. It has to. The universe is full of patterns that look significant but dissolve under scrutiny, apophenia, the human tendency to see connections where none exist. 2 events separated by 3 years is not, on its face, a compelling case for causation. It's a starting point, a hypothesis, something to test. But some members of the working group couldn't shake the feeling that they were looking at something real, something that had been happening quietly, beneath the threshold of detection, and was only now becoming visible because the instruments had improved, the observations had aligned, and someone had thought to check. The data always whispers before it speaks. Meanwhile, outside the formal channels of ESA and NASA, the data was leaking. Not through intentional disclosure, scientists are careful about that, but through the ordinary circulation of research, Conference abstracts, preprint servers, email threads among colleagues. Someone mentioned the 37.8 MHz signal in a seminar. Someone else posted a spectrogram on social media, asking if anyone had seen similar emissions. The amateur astronomy community, which monitors solar activity with surprising sophistication, began searching their own archives. Radio enthusiasts, the kind who build backyard arrays and log mysterious signals for fun, started scanning the 37.8 MHz band, waiting for the hum to return. It didn't. Not in October, not in November, but the absence of the signal became its own kind of evidence. If the hum only appeared in connection with the subcoronal jets, and the jets only appeared in connection with 3I Atlas, then the silence meant something. It meant the phenomenon was specific, repeatable, and linked to an interstellar object that was now millions of kilometers away, coasting outbound toward the heliopause. Which raised a question no one wanted to ask out loud, but everyone was thinking, if 3I Atlas caused the jets, how? A comet is a lump of ice and rock. It has no magnetic field, no internal power source, no mechanism to reach down through 2.9 million kilometers of stellar plasma and trigger jets at depths where nothing should move. Unless it wasn't just a comet, or unless the sun itself was reacting to something we don't yet understand, a process that involves interstellar matter, magnetic memory, and signals that ripple through the star like whispers through stone. The working group's preliminary report, circulated internally on October 20th, concluded with a careful, diplomatic statement. The observed correlation between subcoronal jet activity and 3 Atlas perihelion timing is statistically significant, but lacks a physical mechanism. Further observation and modelling are required. Translation: we see it, we don't understand it, and we need more data. But data, in this case, required time, and the clock was running. Solar Orbiter's observation window was closing. 3I Atlas was fading. The jets had stopped. Whatever had happened beneath the sun on October 9th, it was over. Or so they thought. Chapter 3. The Wake Pattern. Sometimes the answers aren't in the new data. Sometimes they're buried in the old, waiting for someone to ask the right question. On October 14th, Dr. Samuel Okonkwo, a solar physicist at the Goddard Space Flight Center in Maryland, was doing exactly that. He was combing through archived imagery from the Solar and Heliospheric Observatory, SOHO, a spacecraft that has been watching the sun continuously since 1996. SOHO is old by space mission standards, but it's reliable, and its decades of observations provide a baseline that newer missions like Solar Orbiter build upon. Dr. Okonkwo's task was straightforward. Search SOHO's archives for any historical precedent for the subcoronal jets observed on October 9th. He wasn't looking for exact matches, those were unlikely, but for similar events that might offer clues about the physical processes involved. He started with the obvious parameters: jet depth, velocity, and duration. Then he added the oxygen 18 anomaly as a search filter, even though spectroscopic data from SOHO was less precise than what Solar Orbiter could provide. The search returned 37 possible matches spanning 29 years of observation. Most were false positives, coronal jets that superficially resembled the October 9th event, but lacked the depth or chemical signature. Dr. Okonkwo filtered them out, narrowing the list to events that occurred below the convection zone boundary. 3 matches remained, one from 2003, one from 2012, one from 2022. He opened the 2022 file first, knowing from Dr. Rask's earlier report that it was linked to 3I Atlas's perihelion. The imagery was grainy compared to Solar Orbiter's high-resolution scans, but the structure was unmistakable, a cluster of bright jets emerging from deep within the sun, lasting approximately 6 hours, then fading. Then he opened the 2012 file. Another match. Subcoronal jets, deep formation, similar duration, no oxygen 18 anomaly in the spectroscopic data, but SOHO's instruments in 2012 weren't sensitive enough to detect trace isotopic variations. The absence of evidence wasn't evidence of absence. But here's what caught Dr. Okonkwo's attention. The 2012 event occurred on August 16th, during a period of low solar activity. And in the days following the jet event, SOHO's coronagraph, an instrument that blocks the sun's bright disk to reveal the faint corona, had captured images of a faint dust trail passing through the inner heliosphere. a dust trail consistent with a small inbound object, possibly a comet, possibly an asteroid fragment. The data was fragmentary, and no follow-up observations had been conducted. The trail had been noted, logged, and filed as a minor curiosity. Dr. Okonkwo checked the orbital parameters of known comets and near-Earth objects active in August 2012. None matched the dust trail's trajectory, but when he extrapolated the trail backward, calculating where an object on that trajectory would have come from, he found something interesting. The path aligned with the general direction of interstellar space. Not precisely. SOHO's coronagraph data wasn't accurate enough for precise trajectory reconstruction, but suggestively. He opened the 2003 file. Same pattern. Subcoronal jets, a brief magnetic lull, and in the weeks following the event, scattered reports from amateur astronomers of a faint, fast-moving object in the inner solar system. Observed visually, never confirmed by professional telescopes, dismissed as a likely imaging artifact. 3 events, separated by years, each associated with deep solar jets, each occurring around the time a faint object passed through the inner heliosphere. Dr. Okonkwo sat back and considered what he was looking at. Was this evidence of a recurring phenomenon? A pattern that had been playing out for decades, unnoticed because no one had thought to connect solar activity with transient interstellar visitors? Or was it coincidence? The solar system is full of small objects, asteroids, comets, dust streams, passing through the inner heliosphere constantly. Finding a dust trail near any given solar event isn't surprising. It would be stranger if you didn't find one. The challenge in science is distinguishing signal from noise, patterns from pareidolia, meaningful correlations from statistical flukes. Dr. Okonkwo drafted a memo outlining his findings. He included the dates, the imaging data, and the trajectory analysis for the 2012 dust trail. Then he added a speculative section, clearly labelled as such, proposing a hypothesis. If interstellar objects pass through the inner solar system more frequently than current detection methods reveal, their gravitational and magnetic influence could interact with the Sun's subsurface plasma in ways we don't yet understand. The subcoronal jets may represent a form of plasma memory, a delayed response to the passage of an object through the Sun's extended magnetic field. It was cautious, tentative, the kind of hypothesis that doesn't claim certainty but opens the door for further investigation. But it was also radical, because if the Sun could remember the passage of interstellar objects, if those passages left detectable imprints in the subsurface plasma, then the implications extended far beyond solar physics. It would mean the Sun was not a static, isolated star but a dynamic sensor, recording the traffic of objects through its domain in ways we'd never imagined. Dr. Okonkwo sent the memo to his supervisor at Goddard, who forwarded it to colleagues at ESA, JAXA, and the Harvard-Smithsonian Center for Astrophysics. The response was mixed. Some researchers found the hypothesis intriguing, worth exploring through modelling and simulation. Others were skeptical, arguing that the correlation was weak and the mechanism implausible. But one researcher, Dr. Kenji Yamada at JAXA, replied with a single sentence that would stick with Dr. Okonkwo for weeks. It's like the Sun is collecting graffiti from every object that passes by. Interstellar graffiti. The phrase was poetic, almost whimsical. But it captured something essential about the hypothesis. The idea that the Sun wasn't just a passive source of light and heat, but an active recorder, etching the presence of visitors into its deep layers where plasma moves on timescales measured in centuries. If that were true, if the Sun could remember, then the jets on October 9th weren't just a reaction to 3I Atlas's passage. They were an archive, a record, a message from the Sun's interior, surfacing 3 years after the event that caused it. Which raised an uncomfortable question. What else was written down there? What other objects had passed by, undetected, leaving their marks in the plasma depths where we'd never thought to look? Meanwhile, the hypothesis began circulating beyond professional channels. Science journalists picked up on the interstellar graffiti metaphor, writing articles with headlines like, "Is the Sun recording cosmic visitors?" and "Plasma Memory, the Sun's Hidden Archive." The articles were speculative, often oversimplified, but they captured the public imagination. Social media discussions buzzed with questions. Could the Sun store information? Could we read it? What would we find if we looked deeper? Dr. Okonkwo watched the coverage with a mix of satisfaction and unease. He appreciated the interest. Science needs public engagement, but he worried that the speculation was running ahead of the data. The hypothesis was a starting point, not a conclusion. It needed testing, modelling, peer review. It needed to survive the gauntlet of sceptical colleagues who would poke at every assumption and demand rigorous proof. But beneath the professional caution, he felt something else. A quiet excitement. The sense that they were on the edge of understanding something profound about the sun, not just how it works, but what it is. Not a furnace, not a reactor, but a witness, a recorder, a star that remembers. On October 17th, the working group at ESA added Dr. Okonkwo's findings to their internal report, including the 2003 and 2012 events as historical context. They noted the correlation, flagged it as worthy of further study, and added a cautious recommendation. Consider expanding observational campaigns to monitor for future interstellar object transits and associated solar activity. It was a bureaucratic way of saying, we need to pay attention, we need to watch, because something is happening here and we don't want to miss it again. But the clock was still running. Solar Orbiter's window was closing, and if another subcoronal jet event occurred, if the sun's memory surfaced again, they needed to be ready, because the next message might tell them not just where 3i Atlas had been, but where it was going. Chapter 4. The Gold Line from Pixel. Sometimes the universe connects dots you didn't know existed on the same page. On October 17th, NASA's Perseverance rover was parked on the western edge of Jezero crater on Mars, methodically analysing rocks as it had been doing for over 4 years. The rover's mission was to search for signs of ancient microbial life and collect samples for eventual return to Earth. It carried a suite of sophisticated instruments, including Pixel, planetary instrument for X-ray lithochemistry, and Sherlock, scanning habitable environments, with Raman and luminescence for organics and chemicals. Pixel uses X-ray fluorescence to determine the elemental composition of Martian rocks with microscopic precision. Sherlock uses ultraviolet spectroscopy to detect organic molecules and minerals. Together, they form a powerful analytical toolkit for understanding Mars's geologic history. On Sol, 1456, the Martian day count since landing, Perseverance aimed Pixel at a small layered rock the science team had nicknamed Gilded Edge. The rock was unremarkable at first glance. Reddish-brown, wind-eroded, sitting among countless similar rocks scattered across the crater floor. But when Pixel's X-ray scan came back, something unusual appeared in the data. Micrograins embedded in the rock's surface, tiny particles barely a few micrometers across, showed an isotopic signature that didn't match typical Martian material. Specifically, the oxygen isotope ratio was off. Mars has a distinct isotopic fingerprint, shaped by billions of years of atmospheric loss, volcanic activity, and interaction with solar wind. Martian rocks carry that fingerprint in their chemistry. But these micrograins didn't fit. Their oxygen 18 to oxygen 16 ratio was elevated, falling outside the range typical of Martian minerals. Dr. Isha Patel, a geochemist with NASA's Perseverance science team, reviewed the data from her office at the Jet Propulsion Laboratory in California. She cross-referenced the reading with Sherlock's spectroscopy data, which had scanned the same rock moments earlier. Sherlock detected trace amounts of silicate minerals, common on Mars, but also faint organic compounds, likely from ancient water rock interactions. Nothing alarming, but the oxygen 18 ratio was odd enough that Dr. Patel flagged it for further analysis. Then she did what scientists do when they encounter an anomaly. She searched for similar cases. She opened the Perseverance mission's extensive database of rock analyses, looking for other instances where oxygen isotopes had fallen outside the typical Martian range. She found 2, both from earlier in the mission, both from rocks in different regions of Jezero crater. Both flagged as anomalous, but not investigated further because they fell within the margin of measurement uncertainty. But now there were 3, and 3 anomalies start to look less like measurement error and more like a pattern. Dr. Patel ran the isotopic ratios through comparative models, checking them against known sources. Terrestrial contamination, unlikely given the rover's sterilization. Meteoritic material, possible, but the signature didn't match known meteorite types. And cometary debris. Cometary debris was a long shot. Mars's thin atmosphere does capture occasional dust from passing comets, but the amounts are minuscule, and the particles are usually weathered beyond recognition. Still, Dr. Patel pulled up the isotopic profiles of several well-studied comets, including Halley, Hale-Bopp, and 67P Churyumov-Gerasimenko. The match wasn't perfect, but it was close. The oxygen-18 ratios in the Martian micrograins fell within the range observed in cometary ice. Dr. Patel noted this in her report. Then, out of thoroughness, or maybe curiosity, she checked one more source, 3 Atlas. The spectroscopic data from 3 Atlas's 2022 perihelion was publicly available, archived by multiple observatories. Dr. Patel downloaded the files and extracted the oxygen isotope measurements from the comet's coma. The ratio matched. Not approximately. Not within the margin of error. Exactly. She sat back and stared at the screen. The micrograins on a rock in Jezero crater had the same oxygen isotope signature as an interstellar comet that had passed through the inner solar system 3 years ago. Which meant one of two things. Either 3I Atlas's dust had reached Mars, despite the comet's trajectory never bringing it close to the planet, and somehow settled on Jezero crater in a way that deposited grains on multiple rocks across different locations. Or something else was going on. Something that involved the same isotopic signature appearing in multiple places, beneath the Sun, in the solar wind, and now on Mars. Dr. Patel drafted an email to her team lead, Dr. Kenneth Liu. She titled it, Possible Cometary Contamination in Jezero Samples. She kept the language cautious, outlining the isotopic match without speculating about the mechanism. But when Dr. Liu read the report, he did something unusual. He forwarded it to a colleague at NASA's heliophysics division, someone he'd worked with years earlier on a solar wind study. The colleague happened to be on the ESA working group reviewing the October 9th subcoronal jet data. The email chain grew. Within 2 days, the Perseverance findings were circulating among solar physicists, planetary scientists, and orbital dynamicists. And as the data moved between disciplines, a pattern began to crystallize. The oxygen-18 ratio wasn't just appearing in isolated events, it was threading through the solar system like a signature, linking the Sun's interior to Mars's surface to an interstellar visitor that had already departed. On October 20th, a small NASA subcommittee convened to discuss the correlation. The meeting wasn't public. No press release followed. But according to internal memos later obtained through Freedom of Information Act requests, the committee flagged the oxygen-18 thread as a shared isotopic anomaly, warranting cross-mission analysis. Translation: this isn't just interesting, it's significant. But significant in what way? That was the question no one could answer. An isotopic signature, by itself, doesn't imply causation. It doesn't tell you how the signature moved from one place to another. It doesn't reveal mechanism or intent. It's just a fingerprint, and fingerprints only matter if you can connect them to the hand that left them. Still, the fact that the fingerprint appeared in 3 distinct locations, subcoronal jets, Martian rocks, and 3I Atlas's coma, suggested something, a process, a connection, a thread woven through the solar system by forces we didn't yet understand. Some researchers began referring to it informally as the resonance chain, not an official term, not something you'd put in a peer-reviewed paper, but a useful metaphor for thinking about how disparate events might be linked by a common cause. And at the centre of that chain, again and again, was 3I Atlas. Not because it was unique. Interstellar objects pass through the solar system occasionally. Oumuamua and Borisov had done so without triggering solar jets or leaving isotopic traces. But 3I Atlas had done something different, something that left marks. The question was, what? Meanwhile, independent analysts, the kind who operate outside formal institutions, combing through public data for anomalies, started building their own models. They overlaid 3I Atlas's trajectory with solar activity, logs, planetary alignments, and archived spectroscopic data. They found correlations that professional scientists were too cautious to claim. Timing alignments, isotopic matches, magnetic fluctuations. Most of it was noise. Pattern seeking without the rigour of hypothesis testing. But some of it pointed in directions that formal research hadn't yet explored. One analyst, posting on an astronomy forum under the handle Helios Watcher, compiled a timeline that linked every known subcoronal jet event to the trajectories of small inbound objects. The correlation wasn't perfect, but it was suggestive, and buried in the timeline was a footnote. If the sun is reacting to these objects, the reaction isn't instantaneous. There's a delay, like it takes time for the signal to propagate through the star. No one in NASA's official channels cited Helios Watcher, but the idea was already circulating in the working groups. Could the sun's interior act as a kind of slow-motion recorder, where events on the surface, or just beyond it, leave imprints that only surface days, months, or years later? It was speculative. It stretched the boundaries of known stellar physics. But it wasn't impossible, and in science, impossible is a stronger word than people realize. It means you've exhausted the known laws and need new ones. Implausible is different. Implausible just means unlikely, and unlikely things happen all the time in a universe with trillions of stars and more planets than we'll ever count. What was happening with 3I Atlas, the subcoronal jets, and the Oxygen 18 thread was implausible, but it wasn't impossible. Not yet. Chapter 5. Starship's Silent Window. On October 20th, SpaceX launched Starship Flight 17 from the company's Starbase facility in South Texas. It was the latest in a series of test flights aimed at proving the fully reusable heavy-lift rocket's readiness for orbital operations. But Flight 17 carried something new, a solar spectrograph payload developed in partnership with NASA's Marshall Space Flight Center. The instrument was designed to study the sun's corona during periods of high activity, capturing high-resolution spectroscopic data across ultraviolet and X-ray wavelengths. It wasn't a primary mission. Starship was still in the testing phase, but NASA saw an opportunity. Starship's trajectory would take it to an altitude of 380 kilometers, well above most atmospheric interference, and its large payload bay could accommodate instruments that smaller rockets couldn't carry. The spectrograph was mounted in the cargo section, oriented to face the sun during a 20-minute observation window as Starship coasted through apogee. The plan was straightforward: power on the instrument, collect data, transmit it to ground stations, then shut down before re-entry. At 11:37 UT, Starship lifted off. The ascent was smooth. The Super Heavy booster separated cleanly and executed a controlled descent. Landing on the pad as planned, Starship continued to orbit, reaching its target altitude on schedule. At 12:04 UT, the spectrograph powered on. At 12:07 UT, telemetry from Starship stopped. Mission control at SpaceX's Hawthorne facility in California went quiet. Engineers scanned their screens. No signal, no data, no telemetry indicating the spacecraft's position, velocity or status. For 23 minutes, Starship was silent. Then, at 12:30 UT, the signal returned. Telemetry flooded back in, showing that Starship was still in orbit, systems nominal, trajectory unchanged. The spacecraft resumed normal operations, executing its deorbit burn and splashing down in the Pacific as planned. But when engineers reviewed the telemetry data, they found something strange. The downlink during the silent window hadn't been lost. It had been inverted. Telemetry data is transmitted in packets, encoded with timing information that allows ground stations to reconstruct the spacecraft's status. During the 23-minute window, the packets had arrived, but their phase was reversed, as if the signal had been reflected through a mirror. The timestamps were backward. The data checksums were negative values. The signal itself appeared to have travelled from the future to the past, or vice versa. Dr. Lydia Cross, a communications engineer with SpaceX, spent the afternoon trying to make sense of it. She checked for software glitches, satellite interference, ground station malfunctions. None of the usual suspects fit. The phase inversion was clean, consistent across all data streams. It wasn't noise, it wasn't corruption. It was as if the signal had passed through something, some region of space, that flipped its properties before transmitting it back to Earth. Dr. Cross filed a preliminary report, labelling the event as a data compression fault, a catch-all term for anomalies that don't fit neat categories. She noted that the inversion coincided with the spectrograph's observation window, during which Starship had been oriented toward the Sun. But she also added a footnote, buried in the technical appendix. Phase inversion timing aligns with solar observation corridor. Recommend cross-reference with active solar phenomena. That footnote reached a researcher at Lockheed Martin's Advanced Technology Center, who happened to be analysing data from Solar Orbiter's October 9th jet event. The researcher pulled up the telemetry from Starship's silent window and compared it to the magnetic oscillations recorded by Solar Orbiter. The match wasn't exact, but the harmonic structure, the pattern of oscillations, the frequency ratios, was eerily similar, not identical, similar, like an echo of the same signal, transmitted through different mediums. The researcher drafted a memo to colleagues at NASA's Jet Propulsion Laboratory. The memo was cautious, speculative, hedged with caveats. But it proposed a hypothesis. If Starship's telemetry inversion was caused by interaction with a localized magnetic anomaly, possibly a residual field structure from the October 9th subcoronal jets, then the spacecraft may have passed through a region of space where the Sun's magnetic influence extends farther than standard models predict. It was a polite way of saying, something weird happened. We don't know what, but it might be connected to the solar jets. Within days, the hypothesis was circulating among engineers and scientists working on solar missions. Most dismissed it as overthinking a simple telemetry glitch. Spacecraft experience data corruption all the time. Phase inversions, while rare, aren't unprecedented. But a smaller group, those who had been following the 3I Atlas correlation, the oxygen 18 thread, the 37.8 TMS hum, saw it as another piece of the puzzle, another fingerprint, another thread, and once again the timing was suggestive. Starship's observation window, during which the telemetry inverted, occurred as the spacecraft passed through the corridor aligned with the subcoronal jet's emergence. Not proof, not causation, but correlation, and enough correlations start to look like something more. Meanwhile, SpaceX released a public statement about Flight 17, describing it as a successful test, with minor telemetry irregularities during ascent. No mention of the phase inversion, no mention of the silent window. Officially, nothing had happened. But unofficially, in the private email chains and encrypted chats where scientists share unvetted ideas, the conversation was accelerating. What if the subcoronal jets weren't just plasma phenomena? What if they were leaving behind magnetic structures, invisible, transient, but detectable by spacecraft passing through their influence? What if 3 Atlas hadn't just passed by the Sun? What if it had interacted with it in a way that left a persistent field, a wake, a shadow, a memory etched into the fabric of space itself? It was wild speculation, the kind of idea that doesn't survive contact with rigorous modelling. But it was the kind of speculation that drives science forward, because it dares to ask, what if the universe works differently than we think? On October 22nd, Dr. Cross received an email from a researcher at NASA's Goddard Space Flight Center. The email contained a single attachment, a spectrogram from the 3I Atlas observation logs, recorded during the comet's 2022 perihelion. The spectrogram showed harmonic oscillations in the radio spectrum. The frequency ratios matched the phase structure of Starship's inverted telemetry. Not exactly, but close enough that the match couldn't be ignored. Dr. Cross stared at the image for a long time. Then she replied, "What is this thing?" The response came 6 hours later. "I don't know, but I think it's still out there. Some signals hide in the silence between the signals." Chapter 6. The Isotopic Mirror. On October 23rd, NASA's Heliophysics Division held an internal review meeting to discuss the growing body of correlation surrounding 3 Atlas and the October 9th subcoronal jet event. The meeting wasn't public. No media were invited. But according to meeting minutes later obtained through FOA requests, the discussion was intense. The working group had compiled a summary document, distilling weeks of observation and analysis into a single presentation. The document included the subcoronal jets, the 37.8 MHz radio hum, the oxygen 18 anomalies from Mars and the solar wind, the historical SOHO events, and Starship's telemetry inversion. Individually, each event could be explained as a natural phenomenon, an instrumental artifact, or a statistical outlier. But together, they formed a pattern that was harder to dismiss. The centerpiece of the presentation was a graph showing oxygen isotope ratios from 3 sources: the subcoronal jets, Solar Orbiter, cometary material, 3I Atlas coma, and Martian micrograins, Perseverance rover. The ratios aligned. Not perfectly. There were measurement uncertainties, calibration differences between instruments, but within margins that made the alignment statistically significant. A probabilistic analysis, conducted by an independent statistician at MIT, calculated the likelihood of such an alignment occurring by chance. The result? 1 in 22,000. Not impossible, but improbable enough to demand attention. The graph was stark. 3 data points, 3 different sources, 1 signature. Beneath it, a caption read, "Shared isotopic thread, origin unknown." Dr. Moreau, leading the presentation, walked the room through the timeline. October 9th, jets appear. October 11th, radio hum detected. October 14th, Soho archive reveals historical precedents. October 17th, Martian rocks show matching isotopes. October 20th, Starship telemetry inverts in observation corridor. 5 events in 12 days, each unusual on its own. Together, they suggested something systematic. But what? The room debated. Some argued for a natural explanation rooted in solar physics, a previously unobserved convection mode, a deep magnetic instability, a plasma process that occasionally dredges up isotopically anomalous material from the sun's core. Others suggested cometary contamination on a system-wide scale. Perhaps 3I Atlas's tail had been larger than observed, seeding the inner solar system with dust that reached Mars, the sun's atmosphere and near-Earth space. A third group proposed the plasma memory hypothesis, the idea that the sun's interior records the passage of interstellar objects, and the jets were delayed echoes of 3I Atlas's 2022 perihelion. Each explanation had merits, each had flaws. The convection hypothesis didn't explain the timing, why the jets appeared 3 years after 3 Atlas's passage. The contamination hypothesis didn't explain how dust could reach both Mars and the sun's subcoronal layers simultaneously. The plasma memory hypothesis lacked a physical mechanism. No one could explain how the sun would store and later release information about a passing comet. But as the discussion continued, one thread kept surfacing: the math. The 1 in 22,000 probability wasn't just a number, it was a threshold. In science, when the odds of a random correlation drop below certain levels, typically 1 in 1,000 or lower, you start treating the correlation as meaningful, even if you don't understand why. 1 in 22,000 crosses that threshold decisively. Dr. Moreau concluded the meeting with a carefully worded statement. The observed correlations are statistically significant. The mechanism is unclear. Further investigation is warranted, particularly coordinated observation campaigns for future interstellar object transits. It was a diplomat's way of saying, we don't know what's happening, but we can't ignore it. The meeting adjourned. The summary document was classified as internal only, not for public release. But within days, portions of it leaked, anonymously posted to scientific forums, discussed on social media, cited in blog posts by amateur astronomers. The 1 in 22,000 probability became a meme, a shorthand for the mystery, a number that carried weight because it represented not speculation but calculation. And as the number circulated, so did the questions. If the sun is reacting to interstellar objects, what's the mechanism? If the oxygen-18 signature is spreading through the solar system, where did it originate? If 3I Atlas left a wake, what else might be drifting through that wake? Some scientists publicly dismissed the speculation. One prominent solar physicist, in an interview with Scientific American, called the correlations interesting but premature, warning against connecting dots without understanding the lines between them. But others were less cautious. In private conversations, some admitted that the pattern was too strong to ignore. One researcher, quoted anonymously in a Nature News article, said, "The math doesn't lie. Something happened. We just don't know what." And that, in a way, was the most unsettling part. Not that something mysterious had occurred. Science is full of mysteries. But that the mystery involved an object we'd thought we understood, passing through a star we'd studied for centuries, leaving traces we couldn't explain. 3I Atlas had been catalogued as a comet, icy, inactive, predictable. But comets don't leave isotopic fingerprints on Martian rocks. They don't trigger plasma jets deep within stars. They don't invert spacecraft telemetry or hum at 37.8 MHz for 19 minutes. Unless they do, unless we've been wrong about what comets, especially interstellar comets, actually are. On October 25th, Dr. Patel from the Perseverance team published a short preprint on arXiv a platform for sharing scientific papers before peer review. The paper, titled Anomalous Oxygen Isotope Ratios in Jezero Crater Dust Grains, outlined the Martian findings and noted the correlation with 3I Atlas. The paper was cautious, avoiding grand claims, but in the concluding paragraph Dr. Patel wrote, "If the observed isotopic signature originates from an interstellar source, the implications extend beyond planetary science. We may be witnessing evidence of material exchange between stellar systems, a process that, while theoretically possible, has never been observationally confirmed. Material exchange between stellar systems, another way of saying interstellar contamination, or more speculatively, communication. Not communication in the sense of intent, but communication in the sense of information transfer. A comet from another star carrying the chemical signature of its birthplace, depositing that signature in a new system as it passes through. The Sun records it, Mars collects it, spacecraft detect it, and we're left trying to read the message. The preprint was downloaded 12,000 times in its first week. Comments flooded in, ranging from enthusiastic support to harsh criticism. Some praised Dr. Patel for connecting disciplines, planetary science, heliophysics, astrochemistry, in a way that revealed new questions. Others accused her of overstating the significance of noisy data. But the conversation had shifted. What had started as an isolated solar observation was now a system-wide mystery, threading through planets, stars, and the dark between them. And at the centre of it all, moving outward at 27 kilometers per second, was 3I Atlas, still visible, barely, to telescopes sensitive enough to track it, still moving, receding, fading, but not gone, not yet. Chapter 7. The Missing File. Sometimes the most telling evidence is the evidence that disappears. On October 26th, a researcher at the University of Colorado, Dr. Marcus Venn, a graduate student working on heliosismology, was searching NASA's public data archive for solar neutrino measurements. He was building a model of subsurface plasma flows and needed high-resolution neutrino flux data from the Sun's core. NASA's archive is vast, containing decades of observations from hundreds of missions. Most of it is freely accessible, organized by mission, date, and data type. Dr. Venn navigated to the Solar Orbiter dataset, looking for files tagged with neutrino and subsurface. One file caught his attention. 3. Continuum phase, X7 date. The file name was unusual. The 3I prefix suggested a connection to 3I Atlas, but the file was stored in the Solar Orbiter directory, not the small bodies or interstellar objects section. The suffix X7 implied a high-level classification or an experimental dataset. Dr. Venn clicked the download link. The file was gone. Not corrupted, not restricted, deleted. He checked the metadata log, which records every file's upload date, modification history, and access statistics. The logs show that 3I Continuum Phase X7 DAT had been uploaded on October 12th, 3 days after the subcoronal jet event. It had been downloaded once, on October 19th, from an IP address traced to CERN's data center in Switzerland. Then, on October 24th, the file was removed from the archive. No explanation, no replacement. Just gone. Dr. Venn was puzzled. NASA's data policy is transparent. Once a file is uploaded to the public archive, it remains there indefinitely unless it's found to contain errors or sensitive information. Even then, deletions are documented with a note explaining the reason. But this file had vanished without comment. He emailed the archive administrator asking about the deletion. The response came 2 days later. File removed at the request of mission operations, no further details available. That was it. No elaboration, no justification. Dr. Venn mentioned the missing file to his advisor, who suggested he submit a Freedom of Information Act request. FOIA requests are slow, often taking months, but they're a standard tool for accessing government-held information when official channels don't provide answers. Dr. Venn filed the request on October 28th. The response came 6 weeks later. The file had existed, had been classified as internal review only, and had been removed from the public archive pending further analysis. The checksum log confirmed it had been downloaded once from CERN, but the actual data, the content of the file, was not included in the FOIA response. It was classified as mission-sensitive and withheld under exemptions for ongoing scientific investigations. Dr. Venn never saw what was in 3I continuum phase or X7 date, but he wasn't the only one who noticed its disappearance. Word spread among the loose network of researchers following the 3I Atlas correlations. The missing file became a focal point for speculation. What did it contain? Why was it removed? And why had CERN downloaded it before it vanished? CERN, the European Organisation for Nuclear Research, is best known for operating the Large Hadron Collider, the world's most powerful particle accelerator. But CERN also conducts research in astrophysics, including studies of cosmic rays, neutrinos, and high-energy phenomena in space. The fact that CERN had accessed a solar neutrino file related to 3I Atlas suggested the data might involve particle physics, specifically neutrino emissions from the Sun's core. Neutrinos are ghostly particles, nearly massless and almost never interacting with matter. The Sun produces them in vast quantities through nuclear fusion in its core. Billions pass through your body every second, day and night, without leaving a trace. But neutrinos can be detected with the right instruments, and they carry information about the Sun's interior that no other particle can provide. Because neutrinos interact so weakly with matter, they escape the Sun's core almost immediately, travelling at nearly the speed of light. Photons, by contrast, take thousands of years to random walk their way from the core to the surface. If something unusual were happening deep within the Sun, say a localized burst of fusion, a magnetic disruption, or an interaction with external material, neutrinos would be the first signal to reach us. And if 3I continuum phase X7 contained neutrino data showing anomalies coinciding with the October 9th subcoronal jets, that would be significant. Very significant. But the file was gone, and without it, the speculation remained just that. Speculation. Still, the disappearance itself became a data point. In the informal investigations happening outside official channels, the missing file was noted, logged, and discussed. It fit the pattern, evidence surfacing briefly, then vanishing before it could be fully analysed. The 37.8 MHz hum, recorded and then dismissed as terrestrial interference. The Starship telemetry inversion, officially labelled a data compression fault. The oxygen-18 anomalies, flagged but not followed up, and now a neutrino dataset downloaded once from CERN and removed from public access. Each piece of evidence considered alone could be explained away. But together, they suggested something uncomfortable, that the investigation into 3I Atlas and the subcoronal jets was being managed, carefully, quietly, and with increasing discretion. Not covered up, not suppressed, but guided, controlled, kept within certain boundaries. Dr. Venn posted about the missing file on an astronomy forum sharing the checksum log and his FOIA correspondence. The post sparked dozens of replies, ranging from sympathetic frustration to conspiracy theories. Some users speculated that the file contained evidence of artificial structures within 3I Atlas. Others suggested the neutrino data revealed dangerous levels of solar instability that NASA didn't want to publicize. Most of it was noise. But buried in the thread, one commenter wrote, "Files don't disappear unless someone wants them to, and if CERN pulled it, they saw something worth pulling." The tone of the investigation was darkening. What had started as scientific curiosity was beginning to feel like something else. Not paranoia. Scientists are trained to be skeptical, not paranoid, but unease. A sense that the answers were out there, recorded, archived, and documented. But slipping away faster than anyone could reach them. Chapter 8. The Jet Below Light. On October 28th, the European Space Agency published a single image that reignited everything. It was a still frame from Solar Orbiter's Extreme Ultraviolet Imager, captured on October 9th during the subcoronal jet event. The image had been processed, enhanced, and analysed for weeks before its release. What it showed was impossible. The jet, one of the bright plasma streams emerging from deep within the Sun, curved against the direction of solar rotation. That's a physical impossibility. The Sun rotates, dragging its magnetic field and plasma with it. Any jet emerging from the Sun's interior should follow that rotation, curving in the direction of the Sun's spin. It's like water flowing from a rotating sprinkler. The spray always curves in the direction of rotation. But this jet curved the opposite way. The image was accompanied by a technical paper published in the astrophysical journal Letters, describing the observation and attempting to explain it. The authors proposed that the jet had been shaped by an external magnetic structure, a compressed region of the solar wind perhaps, or a transient plasma vortex that temporarily reversed the local magnetic field direction. It was plausible. Magnetic fields can twist, reverse, and interact in complex ways. The Sun is not a simple system. But the explanation felt incomplete, because when you looked closely at the image, really looked, the curvature of the jet wasn't random. It wasn't chaotic, the way turbulent plasma usually behaves. It was smooth, deliberate, as if the jet were bending to avoid something. Dr. Emily Joe, a plasma physicist at MIT, published a response paper 3 days later. In it she wrote, "The observed curvature cannot be fully explained by known magnetic field geometries. The jet's trajectory suggests interaction with a localized persistent magnetic anomaly, one that either preceded the jet's formation or formed simultaneously with it." Then she added a line that caught the attention of everyone following the 3 Atlas mystery. "The jet bends as if dodging something." That phrase, dodging something, spread quickly. It was poetic, almost anthropomorphic, attributing intention to a plasma stream, but it captured the visual impression of the image in a way that technical jargon couldn't. The jet looked like it was avoiding an obstacle. But what obstacle? The Sun's interior is a dense, superheated plasma. There are no solid objects down there, no structures that a jet would need to dodge. Magnetic fields can act like barriers, channeling plasma along specific paths, but they don't create sharp, localized obstacles that require evasive maneuvers. Unless something had entered the Sun, or unless something was embedded in the Sun, left behind by a previous interaction, the speculation was immediate. Could 3 Atlas, or debris from its passage, have interacted with the Sun in a way that left a magnetic imprint? A kind of fossil preserved in the stellar plasma that jets would flow around rather than through. It sounded absurd. Comets don't leave fossils in stars. They evaporate. They dissolve. Their material is absorbed into the stellar atmosphere and redistributed by convection. But if 3I Atlas wasn't just a comet, if it carried something denser, something more persistent, then maybe the rules changed. Simulation teams at several institutions began modelling the observed jet curvature, attempting to reproduce it using standard magneto-hydrodynamic equations. The goal was to find a configuration of magnetic fields that would naturally produce the observed bending without requiring an external obstacle. The simulations failed. No realistic magnetic field configuration within the known parameters of solar physics could bend a jet that's sharply against the direction of rotation unless you added an obstacle, a small localized region of enhanced magnetic field strength, something with a field intensity 10 to 20 times higher than the surrounding plasma. Place that in the path of the jet, and the simulation matched the observation. But where would such a region come from? Magnetic fields on the Sun are generated by the dynamo process, convective motion of electrically conductive plasma. They wax and wane, following the solar cycle. They don't spontaneously form isolated, ultra-strong pockets deep in the interior, unless they're induced by external material. Comets, when they pass close to the Sun, carry their own weak magnetic fields, trapped in the ionized plasma of their comas. Those fields are negligible compared to the Sun's. But if a comet were to pass through the Sun's atmosphere and deposit charged material, dust, ions, complex molecules, that material could, in theory, interact with the local magnetic field, creating a transient enhancement, transient being the key word. Such enhancements should fade within hours or days, swept away by the Sun's convective flows, but the jets appeared 3 years after 3 Atlas's perihelion, which meant either the magnetic enhancement persisted far longer than any model predicted, or it was being continuously refreshed by something still present. On October 30th, Dr. Joe gave a seminar at MIT, presenting her analysis of the jet curvature. The room was packed: students, faculty, visiting researchers, and a handful of journalists who'd heard about the dodging jet through the grapevine. Dr. Joe walked through the data, the simulations, the failed attempts to explain the curvature using standard physics. Then she put up a slide showing the trajectory of 3I Atlas, overlaid with the location of the subcoronal jets. The alignment was striking. The jets emerged in the solar hemisphere that 3I Atlas had passed over during its 2022 perihelion. Not exactly above the comet's closest approach point, stellar plasma convex and rotates, so any material deposited in 2022 would have been redistributed, but close enough to suggest a spatial connection. Dr. Joe concluded her seminar with a statement that was both cautious and provocative. If the jet curvature is caused by a persistent magnetic anomaly, and if that anomaly originated from 3I Atlas's passage, then we may be observing a form of stellar interaction that our models don't currently account for. We need better observations, better models, and, most importantly, better tracking of interstellar objects as they pass through the inner solar system. The seminar ended. The questions began. Some were technical, focused on simulation parameters and magnetic field strengths. Others were broader, touching on the implications of the hypothesis. If the Sun can retain magnetic imprints from passing objects, what else might be embedded in its interior? How many interstellar visitors have passed through, undetected, leaving traces we've never thought to look for? And what happens if one of those visitors returns? The questions hung in the air unanswered, because the only way to answer them was to watch, wait, and hope that 3I Atlas, or something like it, passed by again. Meanwhile, 3 Atlas itself was still out there, faint, distant, moving outbound at 27.3 AU, far beyond the orbit of Neptune, but not invisible, not yet. Chapter 9. The Return of 3 Atlas. On October 30th, the Panoramic Survey Telescope and Rapid Response System, PAN-STARRS, detected an object at 27.3 astronomical units from the Sun. PAN-STARRS is a wide-field telescope in Hawaii, designed to scan the sky for transient events, asteroids, comets, supernovae, and anything else that moves or changes. It's part of a global network of survey telescopes that collectively catalogue millions of objects, tracking their positions and trajectories with precision. The object detected on October 30th was faint, magnitude 23.7, right at the edge of PAN-STARRS' detection limit. But its motion was distinctive, fast, outbound, on a hyperbolic trajectory. The observatory's automated system flagged it as a potential interstellar object and ran a preliminary orbit calculation. The result matched 3I Atlas's predicted position and trajectory, accounting for gravitational perturbations from the outer planets. It was 3I Atlas, still moving, still visible, but something was wrong. The object's velocity was higher than expected, not by much, approximately 0.4 kilometers per second faster than the predicted outbound speed. That's a small difference. But in orbital mechanics, small differences matter. They accumulate over time, shifting trajectories in ways that can't be ignored. The discovery was logged in the Minor Planet Center's database, and follow-up observations were requested from other telescopes. Over the next 3 nights, observatories in Chile, South Africa, and Australia confirmed the detection and refined the orbit. The conclusion was consistent. 3I Atlas had accelerated, not decelerated as you'd expect from a comet losing momentum due to gravitational interactions, accelerated. Dr. Elias Renaud, an orbital dynamicist at the Paris Observatory, reviewed the data and ran the calculations himself. He cross-referenced the new trajectory with the original observations from 2022 and 2023. The acceleration had occurred sometime after perihelion, during the outbound phase when 3I Atlas was moving away from the Sun and fading from view. Most comets decelerate slightly after perihelion due to outgassing drag. Gas escaping from the nucleus exerts a small braking force, but 3I Atlas had done the opposite. Dr. Renaud checked for observational errors, instrument drift and calculation mistakes. He found none. The acceleration was real. He drafted a circular, a brief announcement sent to the professional astronomy community, summarizing the findings. In it, he noted, the observed velocity change is inconsistent with known cometry, outgassing behavior. Possible explanations include asymmetric outgassing from a rotating nucleus, fragment ejection, or interaction with an unmodeled external force. Then he added a sentence that he almost deleted before sending, spectroscopic follow-up is recommended to determine if surface composition has changed since perihelion. The circular was published on November 1st. Within hours, telescopes around the world began targeting 3I Atlas, attempting to capture spectra of its faint light. The results came back over the following week, and they were strange. The spectroscopic data showed hints of residual solar material clinging to 3I Atlas's surface. Not just traces, detectable amounts of ionized oxygen, silicon and iron, consistent with plasma from the Sun's corona. It was as if the comet had reached out and touched the Sun's atmosphere, gathering solar matter on its surface as it passed. But 3 Atlas's closest approach had been 0.38 AU, far outside the Sun's visible corona. There was no mechanism for it to collect solar plasma at that distance, unless the Sun's atmosphere had extended farther than expected during 3 Atlas's passage, or unless 3 Atlas had somehow dipped deeper into the solar environment than its recorded trajectory indicated. Dr. Renaud reviewed the original perihelion observations, looking for any indication that 3 Atlas had deviated from its predicted path. The data was sparse, interstellar objects are faint, and tracking them precisely requires constant observation. But the available data showed no large deviations, which left 2 possibilities. Either 3I Atlas had briefly interacted with an extended solar structure, something like a coronal mass ejection or a high-altitude plasma filament that wasn't directly observed, or the object itself had properties that allowed it to interact with the Sun in ways we don't expect comets to. The latter possibility was speculative, but it fit the pattern: the subcoronal jets, the oxygen-18 anomalies, the magnetic imprint, the telemetry inversion, the missing neutrino file. Everything pointed to 3I Atlas being more than just a comet, not a spacecraft, not artificial, but something different, something that didn't fit the categories we'd built to organize the solar system. On November 3rd, Dr. Renaud received an email from Dr. Rask at ESA. It was brief. "Your circular caught my attention. The solar matter on 3I Atlas. Can you estimate when it was acquired?" Dr. Renaud ran the calculations. Based on the decay rate of ionized plasma exposed to interstellar space, the solar material would have degraded significantly over 3 years. But the spectroscopic data showed it was still present, still detectable, which meant it had been acquired recently, not in 2022 during perihelion, but sometime in the past few months. He replied to Dr. Rask, "The plasma signature suggests acquisition within the last 6 months, but that doesn't make sense. 3I Atlas hasn't been near the Sun since 2022. Dr. Rask's response came an hour later. "Unless the Sun came to it." Dr. Renaud stared at the message. What did that mean? The Sun doesn't move. It's the gravitational anchor of the solar system. Everything else orbits around it, but the Sun's magnetic field extends far beyond its visible surface, carried outward by the solar wind. The heliosphere, the bubble of solar influence, reaches over 100 AU, well beyond the orbits of the outer planets. At 27 AU, 3I Atlas was deep within the heliosphere, bathed in solar wind and magnetic fields. Could the subcoronal jets have emitted material that travelled outward, reaching 3I Atlas even at that distance? Could the oxygen-18 anomalies, the plasma ejections, the magnetic disturbances somehow propagate through the solar wind and deposit material on the comet's surface? It was a stretch. Solar wind travels at 400 to 700 kilometers per second. To reach 3I Atlas at 27 AU would take weeks, and the density of solar wind at that distance is minuscule, far too thin to deposit measurable amounts of plasma on a comet's surface. But what if the jets weren't ordinary solar wind? What if they were something denser, faster, more coherent? What if the Sun had reached out to 3I Atlas, not physically but through a directed stream of charged particles, a beam of plasma threading through the solar system like a line drawn in the dark? It was speculative, implausible, but so was everything else that had happened over the past 3 weeks. Dr. Renaud didn't reply immediately. He spent the evening reviewing the data, running simulations, trying to find a natural explanation that fit the observations. He couldn't. Later that week, a small group of researchers, Dr. Rask, Dr. Renaud, Dr. Zhou, Dr. Patel and a few others, held a virtual meeting. It wasn't official, no institution sponsored it, no agenda was set. It was just a conversation among scientists who'd been following the same mystery from different angles and realized they were all looking at the same thing. They shared data, compared notes, and discussed hypotheses. The tone was careful, skeptical, but open. At one point, Dr. Patel said, "If 3I Atlas is interacting with the Sun in real time, if the jets, the isotopes, the plasma residues are all part of an ongoing process, then the interaction didn't end in 2022. It's still happening." Dr. Zhou replied, or it never stopped. The meeting ended without conclusions, but everyone left with the same feeling. The story wasn't over. The subcoronal jets weren't a one-time event. The oxygen 18 anomalies weren't isolated. 3I Atlas wasn't just passing through. It was still here, still connected, still influencing the sun in ways we were only beginning to see. Every trajectory leaves a fingerprint on the light, to be continued in the full 22,000-word script. I've provided a substantial beginning, approximately 11,000 words covering chapters 1 through 9. Due to the length constraint of a single response, I'll need to continue with the remaining chapters, 10-14, to reach the target of 22,000 words. Would you like me to continue with the second half of the script, completing chapters 10-14 and the closing section? Copy Deep Research Yes, Chapter 10, The Thermal Divide. On November the 1st, the James Webb Space Telescope detected something that shouldn't exist in the vacuum of space. JWST had been tasked with a routine observation campaign, mapping the thermal structure of the outer heliosphere, the region where the sun's influence begins to fade and interstellar space takes over. The observations were part of a long-term study of how solar wind interacts with the interstellar medium, creating the boundary known as the heliopause. The telescope's mid-infrared instrument, MIRE, is exquisitely sensitive to heat signatures. It can detect temperature variations across vast distances, revealing structures invisible to optical telescopes. On November 1st, MIRI was scanning a section of the heliosphere roughly 30 AU from the Sun, slightly beyond Neptune's orbit. What it found was a thermal gradient, a bridge of warmth extending from the Sun's outer corona toward the heliopause, following a narrow corridor through the solar system. Dr. Sarah Curie, an infrared astronomer at the Space Telescope Science Institute in Baltimore, was reviewing the data when she noticed the anomaly. At first, she thought it was an artifact, a ghost image created by instrument noise or scattered light from a nearby bright source. But the signal was persistent. It appeared in multiple observation frames taken hours apart, and it was directional, following a specific path through space. Dr. Curie ran calibration checks. She compared the data to archived MIRI observations from previous campaigns. The thermal gradient hadn't been there before. It was new. She measured its temperature, approximately 3,000 Kelvin at the base, near the Sun's outer corona, tapering gradually to 500 Kelvin at its farthest detected extent, around 35 AU. For context, the ambient temperature of space in the outer solar system is about 40 Kelvin, just above absolute zero. The solar wind, even at great distances, carries some thermal energy, but it dissipates rapidly. By 35 AU, the solar wind is cold, diffuse, barely distinguishable from the interstellar medium. But this gradient was warm, not hot. 3,000 Kelvin is cooler than the Sun's corona, but far warmer than the surrounding space. And it was coherent, forming a continuous structure rather than a scattered cloud of heat. Dr. Curie plotted the gradient's trajectory. It extended outward from the Sun, following a path that curved slightly, tracing an arc through the solar system. She overlaid the trajectory with known planetary orbits, asteroid paths, and cometary tracks. Nothing matched, until she added 3I Atlas's outbound corridor. The thermal gradient followed 3 Atlas's path almost exactly. Dr. Curie sat back and stared at the screen. A heat bridge extending from the Sun to an interstellar comet 27 AU away. A structure that, by all known physics, shouldn't be able to sustain itself in the vacuum of space. She drafted an observation report, carefully documenting the detection and flagging it as anomalous thermal emission, origin unknown. Then she sent it to her supervisor, Dr. Lena Ortiz, with a note. This might be connected to the 3I Atlas observations. Dr. Ortiz read the report and immediately forwarded it to colleagues at NASA's Goddard Space Flight Center, the European Space Agency, and the Harvard-Smithsonian Center for Astrophysics. Within 24 hours, the thermal gradient was being discussed in email chains, video calls, and hastily arranged meetings across the global scientific community. The first question, is it real? JWST is one of the most sophisticated instruments ever built, but even the best instruments can produce artifacts. Scattered light, detector noise, cosmic ray hits. There are countless ways for false signals to appear in astronomical data. But Dr. Curie's calibration was thorough. The signal was clean, consistent, and repeatable. Multiple observation frames showed the same structure. Independent analysis by other teams confirmed the gradient's presence. It was real. The second question, what is it? Thermal energy in space doesn't form bridges. It radiates outward in all directions, dissipating according to the inverse square law. You can't have a narrow beam of heat extending for billions of kilometers without a physical medium to carry it, unless there is a medium. One hypothesis proposed that the gradient traced a stream of solar wind particles, a coherent jet of plasma ejected from the Sun during a coronal mass ejection or similar event. If the jet were dense enough, it could carry thermal energy over large distances before dispersing. But coronal mass ejections are fast, violent, and short-lived. They don't maintain coherent structures for weeks. And JWST's observations showed the gradient persisting for at least 6 days, the duration of the observation campaign. Another hypothesis suggested that the gradient wasn't a beam of heat, but a line of warm dust, particles heated by the Sun and aligned along a specific trajectory. Dust can retain heat longer than gas, especially in vacuum. But where would such a dust trail come from? And why would it align so precisely with 3I Atlas's path? Dr. Khoury and her team ran simulations, modelling various scenarios. They tested coronal mass ejections, dust streams, plasma jets, and magnetic field interactions. None of the models reproduced the observed gradient with the right temperature, length, and persistence, except one. A model proposed by Dr. Zhou at MIT, building on her earlier work on the subcoronal jets. She suggested that the thermal gradient wasn't a beam of heat travelling from the Sun to 3I Atlas. It was a conduit, a temporary channel formed by aligned magnetic field lines, along which charged particles could flow. In this model, the subcoronal jets on October 9th had ejected a burst of plasma into the solar wind. That plasma, instead of dispersing randomly, had followed a pre-existing magnetic structure, a kind of invisible tube formed by the interaction between the Sun's magnetic field and 3I Atlas's weak cometary field during its 2022 perihelion. The magnetic tube would act like a wire, guiding charged particles along a specific path. As the particles flowed, they would heat the surrounding medium through collisions and electromagnetic interactions, creating a detectable thermal gradient. It was an elegant hypothesis. It explained the structure, the temperature, and the alignment with 3 Atlas. But it required something extraordinary, a magnetic field structure that persisted for 3 years, threading through the solar system like a scar left by the comet's passage. Standard models of the Sun's magnetic field don't allow for such persistence. Magnetic field lines are constantly shifting, reconnecting, and reconfiguring as the solar wind moves and the Sun rotates. A field structure formed in 2022 should have been erased within days or weeks, not years. Unless 3I Atlas had left something behind that maintained the structure, a magnetic anchor embedded in the solar wind continuously regenerating the field line as it moved outward with the comet. Dr. Zhou presented her model in a preprint paper titled Persistent Magnetic Conduits in the Heliosphere, Evidence from 3I Atlas Thermal Observations. The paper was cautious, acknowledging the speculative nature of the hypothesis and calling for further observation and modelling. But the core idea resonated. It offered a framework for understanding not just the thermal gradient, but the entire sequence of anomalies. The subcoronal jets, the oxygen 18 thread, the telemetry inversion, the accelerated outbound velocity. All of it could be explained if 3I Atlas wasn't just passing through the solar system. If it was connected to the Sun, magnetically, thermally, chemically, in a way that no other object we'd observed had been. On November 4th, NASA's Heliophysics division issued a brief press release, acknowledging the detection of an unusual thermal structure in the outer heliosphere, and noting that it was under investigation. The release was vague, careful not to overstate the findings or fuel speculation. But the scientific community was already talking. Conference presentations were being rescheduled to discuss the thermal gradient. Preprint servers were flooded with papers proposing mechanisms, running simulations and arguing over interpretations. And in the background, a quieter conversation was happening. Among the researchers who had been following 3I Atlas from the beginning, a consensus was forming. This wasn't a comet, not in any ordinary sense. Comets don't leave magnetic conduits. They don't trigger subcoronal jets years after passing the Sun. They don't deposit isotopic fingerprints across planets and stars. They don't form thermal bridges that sustain themselves for weeks. But if 3I Atlas wasn't a comet, what was it? The question hung over every meeting, every email, every paper, and no one had an answer that fit all the data. Some proposed that 3I Atlas was a fragment of a disrupted exoplanet, ejected from another star system and carrying exotic materials we'd never encountered. Others suggested it was a relic of stellar formation, a primordial object formed before the Sun itself. A few whispered about the possibility, remote, implausible, but impossible to fully dismiss, that 3I Atlas was engineered. Not a spacecraft, but something shaped, designed, or modified by processes we didn't understand. It was the kind of speculation that doesn't appear in peer-reviewed papers. It lives in late-night conversations, in encrypted chats, in the margins of conference notes where scientists write the thoughts they won't say out loud, but it was there, unspoken but present. Because when all the natural explanations fail, when the data points towards something unprecedented, you have to consider the alternatives, even the ones that sound like science fiction. Dr. Curie didn't speculate publicly. She stuck to the data, the observations, the careful language of scientific uncertainty. But in a private email to Dr. Rask, she wrote, "Whatever 3I Atlas is, it's teaching the Sun something, or the Sun is teaching us through it. I don't know which is more unsettling." Dr. Rask didn't reply for 2 days. When she did, her message was simple. We're running out of time to find out. Because the clock was still ticking. Solar Orbiter's observation window was closing. JWST's observation campaign was ending. 3I Atlas was fading, moving farther from the Sun, receding into the dark. And the thermal gradient, the heat bridge connecting star and visitor, was beginning to cool. Within 3 weeks, MIRI's follow-up observations showed the gradient weakening. The temperature was dropping, the structure becoming diffuse. By late November, it would be undetectable, lost in the background noise of the cold outer solar system. Whatever connection had formed between the Sun and 3I Atlas, it was fading. But the evidence remained. The data, the images, the isotopic traces, all of it preserved in archives, waiting for someone to piece together the full story. And somewhere, 27 AU away, 3I Atlas continued its journey outward, carrying with it the residue of the Sun's plasma, the memory of the jets beneath the star, and the unanswered question, what are you? Chapter 11. The Solar Observatory shut down. On November 4th, the National Solar Observatory at Mauna Loa, Hawaii, announced a sudden closure for routine instrument recalibration. The announcement came via a brief press release, posted to the observatory's website at 8:47 a.m. local time. It stated that the facility would be temporarily offline for approximately 10 days while technicians performed scheduled maintenance on the observatory's primary solar telescope and spectrograph systems. Scheduled maintenance closures are common in astronomy. Instruments need periodic calibration, cleaning, and upgrades. There was nothing inherently suspicious about the announcement, except that the closure wasn't scheduled. Dr. Marcus Delgado, a solar physicist who had been using the Mauna Loa facility for a long-term study of solar oscillations, learned about the closure when his observation request was abruptly cancelled. He had been scheduled to collect data on November 5th, and his proposal had been approved weeks in advance. He called the observatory director's office, expecting a brief explanation, maybe an instrument malfunction, an unexpected equipment failure, something mundane. Instead, he was told the closure was administrative and that no further details were available. Dr. Delgado found that odd. Administrative closures typically relate to funding, staffing, or facility access issues, things that are announced well in advance. Sudden, unexplained closures are rare and usually associated with safety concerns or critical equipment failures. He reached out to colleagues who used the facility. None of them had been informed about the closure in advance. Their observation requests had been cancelled with the same vague explanation: routine recalibration. But one colleague, Dr. Yuki Tanaka, the same radio astronomer who had detected the 37.8 MHz hum weeks earlier, mentioned something unusual. She had been in contact with a technician at Mauna Loa who had mentioned, in passing, that the observatory's spectrograph had recorded unauthorized high-frequency signals in the days leading up to the closure. unauthorized signals. That phrase caught Dr. Delgado's attention. Solar observatories detect a wide range of emissions, optical, ultraviolet, X-ray. But high-frequency signals typically refer to radio or microwave emissions, which aren't usually part of Mauna Loa's observational suite. Dr. Delgado pressed for more details, but the technician had been tight-lipped, saying only that the signals were flagged by the monitoring system, and that the data was being reviewed by the facility's technical team. Then the observatory went silent. Not just offline, silent. The usual flow of data from Mauna Loa to the public solar databases stopped. The observatory's social media accounts, which typically posted daily updates on solar activity, went quiet. Even the automated weather station on the observatory's roof stopped transmitting data. It was as if the facility had been sealed off from the outside world. Dr. Delgado and his colleagues exchanged increasingly concerned emails. Was there a security issue, a data breach? Had the observatory detected something sensitive enough to warrant a complete communication blackout? On November 8th, a leaked internal memo appeared on an astronomy forum. The memo, dated November 3rd, one day before the closure, was addressed to the observatory's senior staff and outlined the reason for the shutdown. The memo stated that the observatory's high-frequency radio monitoring system had detected an anomalous repeating signal at 5.4 GHz. The signal had been recorded intermittently over a 5-day period, beginning on October 30th. It repeated every 12 minutes, with a consistent waveform and phase structure. The memo described the signal as non-solar in origin, and noted that its frequency and timing did not match any known satellite, aircraft or terrestrial broadcast source. It recommended immediate instrument recalibration and data review to determine if the signal was an instrumental artifact or a genuine astronomical detection. The memo included a spectrogram, an image showing the signal's frequency, intensity and timing. Dr. Delgado downloaded the image and examined it closely. The 12-minute repetition interval was striking. It suggested a periodic source, something rotating, oscillating or pulsing at a regular rate. Dr. Delgado ran a quick calculation. A 12-minute period corresponds to a rotation rate or orbital period of 720 seconds. He checked catalogues of known astronomical objects with similar periods. Pulsars, variable stars, binary systems, nothing matched. Then he remembered something. A detail from the 3I Atlas observation logs. During the comet's 2022 perihelion, astronomers had measured its rotation period by tracking the brightness variations of its nucleus as it tumbled through space. The rotation period was 11.8 minutes, close to 12 minutes. Close enough. Dr. Delgado pulled up the archived 3I Atlas data and compared the rotation period to the radio signal's 12-minute interval. The match wasn't perfect. 3I Atlas's rotation was slightly faster, but within the margin of uncertainty they were consistent. He drafted an email to Dr. Rask attaching the leaked memo and the rotation period comparison. His message was brief. The Mauna Loa signal matches 3I Atlas's rotation. I don't think this is a coincidence, Dr. Rask replied within an hour. Neither do I. Meanwhile, the leaked memo was spreading. Astronomy forums, social media groups, and science news sites picked up the story. Headlines range from cautious, solar observatory detects unexplained radio signal, to sensational, mystery signal from interstellar object shuts down telescope. The National Solar Observatory issued a follow-up statement on November 9th, acknowledging that anomalous signals were detected during routine monitoring, but emphasizing that preliminary analysis suggests the signals are likely instrumental in origin. The statement concluded by reiterating that the facility would reopen once calibration was complete. But the statement raised more questions than it answered. If the signals were instrumental artifacts, why the sudden closure? Why the communication blackout? And why the reluctance to release the data for independent analysis? Some researchers accepted the official explanation. Instrument glitches happen. Observatories shut down to fix them. It's part of the normal operations of scientific facilities. But others, those who had been following the 3I Atlas correlations, saw the closure as part of a pattern. Evidence surfacing, then disappearing. Data detected, then classified. Anomalies observed, then dismissed. It felt like the investigation was being managed, not suppressed, nothing so crude as a cover-up, but guided, contained, kept within controlled channels. Dr. Tanaka, reviewing the leaked spectrogram in her office at the National Radio Astronomy Observatory, noticed something else. The 5.4 GHz signal wasn't random noise, it had structure, harmonic overtones, phase modulations, patterns that suggested a complex source. She ran the spectrogram through an analysis program designed to detect coherent signals in radio data. The program flagged the signal as potentially non-random, with a confidence level of 87%. Non-random. That's a loaded term in radio astronomy. It means the signal carries information, structure, pattern, order. It's the opposite of noise. It doesn't necessarily mean intelligence. Natural processes can produce structured signals. Pulsars emit precise radio pulses, masers create coherent microwave emissions, and magnetized objects generate organized radiation patterns. But non-random signals always demand investigation, because sometimes, rarely, but sometimes, they indicate something extraordinary. Dr. Tanaka wrote a short analysis paper and submitted it to the Astrophysical Journal. The paper described the 5.4 GHz signal, noted its 12-minute periodicity, and proposed that it might be associated with 3I Atlas's rotation. She avoided speculation about what the signal was. She focused on what it wasn't: random, terrestrial, or consistent with known solar emissions. The paper was peer-reviewed, revised, and accepted within 3 weeks, unusually fast for a scientific journal, suggesting that the editors recognized the significance of the findings. When the paper was published in early December, it reignited the conversation. The 5.4 GHz signal became another data point in the growing constellation of anomalies surrounding 3I Atlas. But by then, the signal itself had vanished. Follow-up observations by radio telescopes around the world detected nothing at 5.4 GHz. The 12-minute pulse was gone, as if it had never existed, except for the data. The recordings, the spectrograms, the leaked memos, evidence that something had been there, briefly, pulsing in the radio darkness. And then silence. Expanded script. Chapter 12, November 6th, the harmonic map. On November 6th, a team at CERN, the European Organisation for Nuclear Research, made a discovery that shifted the entire investigation. The team was led by Dr. Isabelle Laurent, a particle physicist specialising in neutrino detection. She had been analysing data from the IceCube Neutrino Observatory, a massive detector buried in the Antarctic ice, designed to capture high-energy neutrinos from space. Neutrinos are elusive. They pass through matter almost without interacting, making them incredibly difficult to detect. But when a neutrino does interact, colliding with an atom in water or ice, it produces a flash of light that can be captured by sensitive detectors. IceCube had been operating continuously for years, cataloguing neutrinos from supernovae, black holes, and other cosmic sources. Dr. Laurent's task was to search for patterns in the neutrino arrival times and directions, looking for correlations that might reveal previously unknown astrophysical processes. On November the 6th, she found one. A series of neutrino events detected over a 3-year period showed a subtle but consistent pattern. The neutrinos arrived in clusters, spaced at irregular intervals but always from roughly the same region of the sky. The direction of the Sun. Solar neutrinos are common. The Sun produces them constantly through nuclear fusion. But these neutrinos were different. They were higher energy than typical solar neutrinos, and their arrival times didn't match the steady stream expected from the Sun's core. Instead, they arrived in bursts, brief, intense pulses lasting minutes to hours, separated by weeks or months. Dr. Laurent cross-referenced the neutrino burst times with solar activity logs, looking for correlations with flares, coronal mass ejections, or other energetic events. Some bursts aligned with solar activity, but others didn't. They occurred during periods of solar quiet, times when the Sun was magnetically calm, with no significant flares or eruptions. Those bursts puzzled her. Where were they coming from? She expanded her search, overlaying the neutrino data with the 3I Atlas observation timeline, and there it was, a match. The anomalous neutrino bursts coincided with the dates of the subcoronal jet events, October the 9th, 2025, September 14th, 2022, and 2 earlier dates, 2012 and 2003, that matched the historical jet events identified by Dr. Okonkwo in the Soho archives. 4 neutrino bursts, 4 subcoronal jet events. The correlation was precise. Dr. Laurent pulled the neutrino energy spectra and analysed them in detail. The bursts weren't random. They had structure, harmonic patterns, frequency ratios that repeated across all 4 events. She ran the data through a Fourier transform, a mathematical technique that decomposes signals into their constituent frequencies. What emerged was striking. A 3-dimensional lattice of harmonic resonances, each node corresponding to a specific time and direction. When plotted spatially, the nodes formed a map. Not a random scatter, but an organised structure anchored near the Sun and extending outward through the heliosphere. Each node corresponded to a historical solar anomaly. The subcoronal jet events, the 37.8 MHz radio hums, the oxygen 18 isotopic spikes. Together they traced a path, a trajectory through the solar system that aligned with 3I Atlas's orbit. Dr. Laurent stared at the map. It looked deliberate, intentional, as if something had been leaving markers, breadcrumbs, scattered through space and time. She shared the data with her colleagues at CERN. The response was immediate and divided. Some saw the pattern as confirmation of a recurring astrophysical process, perhaps a magnetic interaction between the Sun and passing interstellar objects. Others saw it as a statistical artifact, the result of confirmation bias and overfitting the data. But one researcher, Dr. Anton Kuznetsov, a mathematician specializing in signal analysis, saw something else. He noticed that the harmonic map wasn't just a record of past events, it had predictive structure. If the pattern held, another neutrino burst, another event in the sequence, should occur in mid-November, around the 14th or 15th. Dr. Laurent was skeptical. Predicting astronomical events based on limited data is risky. Patterns can deceive. But the mathematics were compelling. She alerted IceCube's operations team, asking them to monitor for any unusual neutrino activity in the coming days. She also sent a summary of her findings to colleagues at NASA, ESA, and the solar observatories still tracking 3I Atlas. The message was cautious but clear. If the harmonic pattern is real, we should see another event within the next 10 days. On November 14th, IceCube detected a neutrino burst. It lasted 8 minutes. The energy spectrum matched the previous bursts. The direction pointed toward the Sun, and Solar Orbiter, still in its observation window, recorded a brief magnetic disturbance in the solar corona. Nothing as dramatic as the October 9th jets, but a measurable fluctuation that hadn't been present moments before. The prediction had held. Dr. Laurent drafted a paper immediately, documenting the harmonic map, the neutrino bursts, and the successful prediction. The paper was submitted to Nature Physics and flagged as high priority by the editors. But before the paper could be published, the data began circulating informally. Researchers shared the harmonic map in private emails, discussing its implications in video calls and conference presentations. The map suggested that 3 Atlas hadn't just passed through the solar system. It had left a trail, a resonance structure embedded in the Sun's magnetic field and neutrino emissions, persisting long after the comet itself had moved on. Some called it a footprint, others called it a signature, and a few in hushed conversations called it a message. Not a message in the sense of language or symbols, but a message in the sense of information, data encoded in the structure of space, left by an object that knew, or was designed to ensure, that it would be detected. It was a provocative idea. It implied intent, and intent implied intelligence, or at least a process shaped by something more than random chance. Most scientists recoiled from that implication. The leap from structured data to intentional message is vast, requiring evidence far beyond what the harmonic map provided. Patterns exist everywhere in nature. The universe is full of order that emerges from chaos without needing design. But the pattern was undeniable, and its predictive power, the fact that it had successfully forecasted the November 14th event, suggested it wasn't just noise. Dr. Laurent concluded her paper with a carefully worded statement. The observed harmonic structure in neutrino emissions and solar magnetic activity correlates strongly with the trajectory and timing of 3I Atlas. Whether this structure represents a natural astrophysical process or a phenomenon requiring new theoretical frameworks remains an open question. Continued observation and modelling are essential. It was a diplomatic way of saying, we see something, we don't understand it, and we need to keep looking. Nothing vanishes in the dark, it just changes frequency. Chapter 13. The Shadow Beneath the Star. On November 9th, as solar activity reached a brief but intense peak, the subcoronal jets returned. Not as dramatically as on October 9th, but unmistakably. Solar Orbiter's instruments detected a cluster of plasma streams emerging from deep within the Sun, originating from the same subcoronal depth, 2.9 million kilometers beneath the visible surface. This time the jets were brighter, denser, and for the first time they were visible not just in ultraviolet and X-ray wavelengths, but in optical light, the range of the spectrum human eyes can see. That shouldn't be possible. Subcoronal plasma is too hot and too deep to emit visible light that reaches space. It should be absorbed, scattered, and reprocessed by the overlying layers of the Sun's atmosphere long before it becomes visible. But on November 9th, observers using ground-based solar telescopes equipped with specialized filters reported seeing faint, bright threads within the solar corona, structures that corresponded exactly to Solar Orbiter's subcoronal jet detections. For a few hours we could see what was happening beneath the Sun. Dr. Rask was at her desk in Darmstadt when the alerts began flooding in. Solar observatories around the world were reporting the same phenomenon. Visible jets, emerging in the same region where the October jets had appeared. She pulled up the real-time data from Solar Orbiter. The EUI imager was capturing the jets in unprecedented detail, and the SPICE spectrograph was analysing their composition. And then she saw it. Within the brightest jet, barely visible against the overwhelming glare of the Sun, was an outline, a geometric pattern. Not a random plasma swirl, not a chaotic magnetic tangle, but something with structure. It looked almost like architecture, angular, precise, as if something solid were embedded beneath the Sun's surface and the jets were tracing its edges. Dr. Rask zoomed in, adjusted the image contrast and applied false color enhancement to bring out faint details. The outline persisted. It wasn't an artifact. It wasn't an optical illusion. It was there. She immediately shared the image with the Solar Orbiter science team, flagging it as urgent review required. Within minutes, the team was in a video call analysing the image from different workstations across Europe and the United States. The consensus was cautious but unavoidable. The structure was real. It appeared to be a localised region of enhanced brightness, shaped by magnetic fields into a geometry that didn't match any known solar phenomenon. Dr. Moreau, leading the discussion, proposed a hypothesis. The structure was a magnetic cage, a configuration of field lines that had trapped plasma in a specific geometry. Such configurations are rare but not unknown. They can form when multiple magnetic flux tubes interact, creating stable pockets of plasma that resist convective mixing. But the geometry was unusual, too regular, too organised. Dr. Zhou, joining the call from MIT, offered a different interpretation. The structure wasn't forming naturally. It was being shaped by an external influence, something embedded in the Sun's interior, distorting the magnetic field around it. She didn't say what that something might be. She didn't need to. Everyone on the call was thinking the same thing. 3i Atlas, or whatever 3i Atlas had left behind. The discussion grew intense. Some argued that attributing the structure to an external object required extraordinary evidence they didn't yet have. Others countered that ignoring the correlation was equally unscientific. The data pointed to a connection, and dismissing it simply because it was unprecedented was a failure of imagination. Dr. Rask listened to the debate, saying little. She was staring at the image, the bright threads within the Sun, the outline of something beneath the surface, and she realised, we're looking at a shadow. Not a shadow in the usual sense, darkness cast by blocking light, but an inverse shadow, a region where light was enhanced, sculpted, revealing the presence of something we couldn't see directly. She typed a message into the call's chat. It's not forming, it's revealing. The jets are showing us something that's already there. The call went quiet for a moment. Then Dr. Moreau replied, "What do you mean?" Dr. Rask chose her words carefully. If the magnetic structure is persistent, if it's been there since 3 Atlas's perihelion, then it's been invisible until now. The jets aren't creating the structure, they're illuminating it, like shining a light into fog. The metaphor resonated. The jets were acting like a tracer, flowing around an obstacle and revealing its shape through their distortion, which meant the structure beneath the sun, whatever it was, had been there all along, hidden in the plasma depths, invisible until the jets emerged and outlined its presence. But what was it? A magnetic fossil, a region of anomalous density, a chunk of debris from 3I Atlas, somehow surviving in the stellar interior despite temperatures that should vaporize any solid matter, or something else. The call ended without conclusions, but Dr. Rask saved the image, the outline of the structure beneath the sun, and sent it to her personal archive with a file name: Shadow Structure Nov Nond PNG. She didn't share it publicly, not yet. The image was too striking, too provocative. It would invite speculation that the data couldn't yet support, but she knew it would leak eventually. Images like that always do. On November 11th, the jets began to fade. Solar Orbiter's instruments tracked their decline over several hours, watching as the bright threads dimmed and the visible structure disappeared back into the depths. By the morning of November 12th, the jets were gone. The sun's corona returned to normal. The shadow beneath the star vanished, but the image remained, and in the days that followed, it circulated, first among the Solar Orbiter team, then to colleagues at other institutions, and finally, inevitably, to the public. The image appeared on social media, in news articles, on astronomy blogs. It was analysed, debated, and dissected. Some saw it as proof of something extraordinary, a relic, a structure, a message from beyond. Others dismissed it as pareidolia, the human tendency to see patterns in randomness. NASA issued a brief statement on November 15th, acknowledging the detection of enhanced magnetic structures in the solar corona, and noting that further analysis is ongoing. The statement was careful, avoiding any mention of 3I Atlas or the speculation swirling around the image, but the statement couldn't contain the conversation. The shadow beneath the sun had been seen. The question, what is it, had been asked, and no answer, official or otherwise, could put that question to rest. Chapter 14. The Reflection in the Light. On November 12th, Solar Orbiter transmitted its final data from the observation window before entering recalibration mode. The data included the last moments of the subcoronal jets, captured as they collapsed inward on November 11th. The jets didn't simply fade, they retracted, pulling back into the sun's interior as if being drawn by an invisible force. Dr. Rask reviewed the footage, watching the jets shrink and converge. They moved in unison, following curved paths that spiraled toward a single point deep within the sun, and then, for a brief moment, less than 3 seconds, the jets merged into a single luminous thread, a bright line extending from the sun's surface down into the subcoronal depths, glowing with an intensity that registered at the upper limit of Solar Orbiter's detectors. Dr. Rask enhanced the image, increasing the contrast to bring out faint details. What she saw took her breath away. The thread wasn't just bright, it was structured. The light it emitted had a pattern, a spectral signature that didn't match normal solar emissions. She ran the spectrum through SPICE's analysis software. The result was impossible. The thread spectrum was inverted. It emitted light at wavelengths where the sun normally absorbs light, and absorbed light at wavelengths where the sun normally emits. It was a negative, a photographic inverse of sunlight itself. Dr. Rask checked the instruments. No errors, no calibration drift. The data was clean. She pulled up archived solar spectra, comparing the thread's emission to decades of observations. The inversion was unprecedented. Nothing in the scientific literature described a solar phenomenon that produced a negative spectrum. But there was a precedent, just not in solar physics. In 2022, during 3I Atlas's perihelion, ground-based spectrographs had captured a brief, unusual emission from the comet's coma. The emission had been noted as an anomaly, but not investigated further. Dr. Rask found the archived spectrum and overlaid it with the thread's emission. The match was exact. The thread beneath the sun was emitting the same inverted spectrum that 3I Atlas had produced 3 years earlier. Dr. Rask sat in silence, staring at the overlaid spectra. The correlation was too precise to be coincidence. The sun wasn't just reacting to 3I Atlas. It was reflecting it, echoing it, responding to the comet's presence with a signal that mirrored the comet's own light. She drafted an urgent message to Dr. Moreau. The thread spectrum matches 3i Atlas. This isn't plasma, it's a feedback pulse. The sun is answering back. Dr. Moreau replied within minutes. Are you sure? Dr. Rask sent the spectral comparison. See for yourself. The data spread quickly through the working group. Within hours, researchers at NASA, JAXA and ESA were analysing the spectrum, running their own comparisons, checking for errors. None were found. The spectrum was real. The inversion was real. The match with 3i Atlas was real. But what did it mean? One interpretation, proposed by Dr. Joe, was that the Sun had absorbed material from 3i Atlas during the comet's 2022 perihelion. Particles, ions, or complex molecules that had been integrated into the solar plasma. When the jets emerged, they carried that material back to the surface, releasing it in a burst that reproduced the comet's original spectral signature. It was a plausible physical mechanism. It didn't require anything exotic, just the ordinary processes of plasma convection and magnetic transport, operating over long timescales. But it didn't explain the inversion. Why would the spectrum be negative? Why would the sun emit light at wavelengths it normally absorbs? Another interpretation, more speculative, was that the sun was responding to 3i Atlas in a way that involved quantum processes, interactions at the atomic or subatomic level that produced anomalous photon emissions. It was far-fetched, requiring physics beyond the standard models, but it offered a framework for understanding the inversion. A third interpretation, discussed only in private, was that the sun was being influenced, actively, deliberately, by 3i Atlas, or by something 3i Atlas represented. That the spectral inversion wasn't a passive reflection but an active response, a message. Dr. Rask didn't subscribe to that interpretation. She was a scientist, trained to favour the simplest explanations that fit the data. Messages required intent. Intent required intelligence, and there was no evidence for intelligence, only for correlation, structure, and patterns that defied easy explanation. But the thought lingered, because the pattern was so precise, the timing so deliberate, the spectrum so perfectly inverted. It felt less like a natural phenomenon and more like a conversation. On November 14th, the thread spectrum was published in a brief preprint, authored by Dr. Rask and the Solar Orbiter team. The paper described the inversion, noted the match with 3i Atlas, and concluded with a single sentence. The origin of the inverted spectrum remains unexplained and warrants further investigation. It was the most cautious way possible of saying, we have no idea what this is. The preprint was downloaded 50,000 times in its first week. Comments flooded in from researchers across disciplines, astrophysics, plasma physics, quantum optics, even theoretical computer science. Everyone had a theory. No one had proof. And then, on November 16th, the signal faded. Solar Orbiter's final transmissions showed the thread dimming, its luminosity dropping until it merged back into the background glow of the sun's interior. The inverted spectrum vanished. The feedback pulse, if that's what it was, ended. Silence returned. The sun resumed its normal rhythms. Solar Orbiter entered recalibration mode, its instruments powered down, its observation window closed, and 3 Atlas, now 28 AU from the sun, continued its journey outward, too faint to track with most telescopes, fading into the darkness between stars. The investigation wasn't over. Papers were still being written, models refined, debates continuing. But the active phase, the period of real-time observation, of events unfolding, had ended. We were left with data, terabytes of images, spectra, magnetic field measurements, neutrino detections, isotopic analyses, a vast archive of information documenting 7 weeks during which something extraordinary had happened, something that connected an interstellar visitor to the star at the centre of our solar system, something that left shadows beneath the sun, isotopic fingerprints on Mars, thermal bridges in space, and spectral inversions that defied explanation. Something we didn't understand, but something we had witnessed. Some mysteries don't end. We began this story on October 9th, 2025, with a cluster of jets emerging from impossible depths beneath the sun. We end it in mid-November, with those jets fading, the signals silencing, and 3i Atlas receding into the dark, but the story doesn't end. Not really, because the data remains, the correlations remain, the questions remain. What is 3i Atlas? A comet, or something more? A natural object formed in the cold regions of another star's planetary system, or a relic of processes we don't yet understand? Why did it interact with the Sun in ways no other object has? Why did it leave isotopic traces, magnetic structures, thermal bridges, and spectral inversions scattered through the solar system like breadcrumbs? And why, 3 years after passing the Sun, does its influence persist? Some will say the correlations are coincidence, that we've mistaken pattern for meaning, signal for noise, that 3i Atlas was just a comet, and everything else, the jets, the anomalies, the shadows, were unrelated solar phenomena that happened to overlap in time. It's a reasonable position. Science requires skepticism, it demands rigour, and extraordinary claims require extraordinary evidence. But the evidence is there, not extraordinary perhaps, not conclusive, but suggestive, compelling, enough to make you wonder, enough to make you look up at the Sun, our familiar, constant, life-giving star, and realise how little we truly know about it, about what moves through it, about what it remembers. The next solar observation window opens in 6 months. New instruments will be deployed, new telescopes will scan the heliosphere, and if 3i Atlas, or something like it, returns, we'll be watching. Because we've learned something from these 7 weeks. We've learned that the solar system is not a static place. It's a dynamic environment shaped by visitors from beyond, by interactions we're only beginning to detect, by processes that bridge the gap between stars. We've learned that the Sun is not just a furnace. It's a recorder, a witness, a participant in the cosmic traffic that flows through the galaxy. And we've learned that some mysteries don't end. They just pass behind the light, waiting for the next observation, the next clue, the next moment when the universe decides to show us something we didn't know we were looking for. This is not science fiction. This is November 2025, and the story is still unfolding. Hit subscribe, keep watching. Tell me where you're listening from, because when the next signal comes, when the next shadow emerges beneath the Sun, we'll be here, following the data, asking the questions, and searching for answers in the light and the darkness. I'm your host, and this is Beyond the Solar Veil. Some mysteries don't end, they just change frequency, and we'll be listening.